So good morning, everyone. Thank you very much for inviting me to this. It's been a nice workshop so far. In the last 2 days, I've noticed that the crowd is more diverse than my usual crowd. And so the talk has sort of morphed through the night into something more like a bit more tutorial-esque as well, but also describing this like recent events. I hope for the experts in statistical learning theory in the audience, you will bear with me. And everyone else, please raise your hands. This is work that's sort of cooking, and I'm happy to give feedback on it. So I'm looking forward to that here. All right, so let's get going, because I have no idea how long this talk is. What's the motivation for this work? Carolina, sorry, I didn't even mention Carolina. So this is joint work with Carolina, who's in the second row here. For a long time, we've worked on understanding generalization in deep learning, whatever that means. And something that has always been a roadblock is that deep learning generalization depends on the data, but we don't have a good way of talking about data. So we have no good way yet of modeling real data. So yeah, you can have mixtures of Gaussians, or class conditional Gaussians, or like a big Gaussian blob or something like that. And maybe some universality result will save us. That would be really awesome if that's true. But there's always a point in statistical analysis where you get down to the data. And I'd yet to see a way of thinking about measuring the complexity of data that felt nice. And we kind of happened upon one, which I'm curious what you'll think about. And it was born out of some work by a group that involves some researchers in Israel and at TTIC. So I'll get to that later. On the other hand, empirical neural scaling laws predict the performance of deep learning across a wide range of network sizes, scale of data, scale of models, et cetera. And so it's interesting to ask, what do these scaling laws potentially tell us about the complexity of data? So I'll kind of make that more precise in a moment. So this is a mix of let's make some progress on understanding deep learning from a statistical angle, and two, wouldn't it be nice to connect it to some empirical phenomena as well, besides the fact that we need to get risk bounds that say something. And that's really a theme of our work for a long time, which is working on theory, but also trying to connect it to empirical phenomena. All right, so here's a little toy theory story about how maybe scaling laws would provide evidence for complexity if you had statistical upper bounds. So let's let R of theta be the risk, say the probability misclassification of a predictor theta. You can think about theta as parameters that are, I'm going to kind of identify parameters with the predictors themselves. Let's theta hat n be the predictor produced by our learning algorithm, like say some neural network training algorithm, given n data and training on a model of size m of n. All right, now let's say I have a theorem of the following form. For every data distribution, there exists a function c epsilon, and this function is going to depend also on like how the architectures change as you give it more data, potentially. So implicitly, there's some kind of choice of architectures here. But yeah, so for every data distribution in this kind of sequence of architectures, there exists a function c epsilon such that with high probability, the risk of your learned predictor is this balance between what looks like an approximation error and what looks like an estimation error. And this rate here is indicative of something that looks like sort of a kind of fast rate or Bernstein kind of thing going on. So this complexity function here is going to dictate the overall rate of this. Yeah, so we have a square root of n term, but I'm actually balancing these two terms as I go. And so the rate at which c epsilon grows as epsilon shrinks to 0 is going to dictate the overall rate. So if c epsilon grows very slowly, like polylog or constant, I'm going to get a 1 over n rate in this case. If it grows polynomially, it's going to give me what looks like a kind of potentially, depending on the size of p, non-parametric rate, like something maybe slower than 1 over square root of n. And if it grows incredibly fast, then I might get a rate that would make us all cry. So, all right, so this is the connection with scaling laws. Is if a scaling law for n data in size m of n model says risk decay is slower than n to the minus 1 over p plus 1, then we get to rule out C epsilon as characterizing the complexity of our data. Yeah?
I know this is a stupid question, but should I have an intuition for what epsilon might mean?
Oh, no, epsilon, yes. Let me offer some. And maybe I'll just I don't know, sometimes you want to hide this, hide the punchline until later, but I think generally it's best to just give it up early. So let's think about epsilon should be the approximation error. So it's I'm going to pick something like a size of architecture, and that's going to dictate how well I can fit the decision boundary. So epsilon is saying, find me an architecture, find me the smallest architecture, and that's what C epsilon is going to be, sort of like the size of that architecture, which can deliver me epsilon approximation error. And then this is going to be the cost I pay for fitting that. So this is the complexity of the architecture. This is the approximation error, and this will be my bound. So,
sorry,
you see,
short related question. So in a way, we should be thinking that M of n has been chosen optimally, so that it's the minimal one that gives us the epsilon for the
potentially. I mean, with a scaling law, you would have done that optimization. But oftentimes in the search for a scaling law, they will have actually collected data off of the optimal path, and so I could potentially evaluate this also on a non-optimal path. I'd love to talk to more people about whether if MN is not optimized, I think I can still rule out I think I can still make a claim logically that the data don't have this complexity. It's just I'd be wasting computation or something else would be going on. All right, so here are the two takeaways here. Maybe that any such function C epsilon can be viewed as a whole function. Now, it's not like a number. It's not like your data is 4. That's how hard your data is 4, right? So, well, though, okay, to be fair, if it reduces to the rate, then there is a number. It's p. Okay, but I'm not sure if it's going to look like that. But any such function C epsilon can be viewed as quantifying the complexity of data in view of this bound. And then scaling laws can provide evidence of complexity. Because if you notice that a slower decay than a prescribed rate rules out something. And given an upper bound, I can't do it the other way. I can't say, oh, your data is simpler than this. I can only really kind of argue for complexity. Just something we thought was interesting. So, all right, so moving on. So what's the kind of approach of this work? So we're going to propose to measure the complexity of data in terms of, roughly speaking, the size, C epsilon of the smallest network that achieves epsilon risk. Not exactly, but close. And then we have 4, what are these called? Courses to this talk. And I'm not sure why I happened upon an Italian metaphor here. But at 5 p.m., when I was desperately trying to figure out a theme, that's what came to my mind. Maybe I was hungry. So, Antipasti. So we're going to study a toy model of neural network training where the output of learning is a randomly initialized neural network that interpolates the data. And this has been studied empirically recently, and our work really was sort of kicked off by a theory paper showing up on the subject. So we're going to assume that some teacher network has 0 risk. So you might call this a realizable setting. And a conclusion that Buzaglo et al. Came to in recent work that was highlighted at ICML was that the number of teacher parameters determines the sample complexity rather than the number of student parameters, which is interesting. And will really change, it tells you a lot of things, right? It gives you a hint for why over-parameterization is maybe not so bad. It gives you a hint for, it would change the nature of it would change what you should be measuring potentially in your scaling law, et cetera. All right, so one caveat here is that to do this, outside of a special case, they have to quantize the weights in one particular case, like a 2-layer network, they're able to give an argument that doesn't require quantization, but they have to introduce the notion of margin. But anyways, I'll return much later to this issue of quantization. So what I mean by that is the neural network weights are not going to be float. Well, they could be float 32. That's going to be log 2 to the 32, nats. Kind of painful to put that number into your bound. but yeah, doing that sort of sidesteps the real issue, which is that that's not the real complexity. All right, so for the preemie, we're going to study a less toy model. We're going to study a sample from the Gibbs posterior rather than a sample from a randomly initialized neural network that fits the data. You can think about the first model as the case where the inverse temperature diverges to infinity. And there should be a log here. So when this diverges to infinity, it recovers this case. All right, and we're going to drop the assumption that some teacher network has zero risk. So we're going to move into this like agnostic setting, and that's going to be essential for getting a law that can tell me about some trade-off between approximation error and estimation error. Because if I have a teacher of some finite size that fits the decision boundary perfectly, there's no trade-off. I'm going to get, and if I have no Bayes error, I'm going to get 1 over n rate. If I have Bayes error, I'm going to get 1 over square root of n rate, and that's not the rates you see in scaling laws. So that's not the situation we're in. So we are in a situation where there's some trade-off between approximation error and estimation error, it seems. I think we could probably maybe logically, if you trust the scaling laws, we can rule that out. All right, and maybe the conclusion of this section will be the number of teacher parameters, again, determines the sample complexity, but now it's to drive the excess risk to some levels. Excess risk means how much worse am I than some teacher? Well, the size of the teacher dictates that. And some bonus is that we've done some very preliminary experiments on MNIST, and you get some non-vacuous bounds, which is they're not impressive non-vacuous bounds because people have been working on this stuff for a while, and there's sort of tricks you can do if you want non-vacuous bounds that kind of move you away from bounds that are useful for actual scientific understanding, and maybe and move you towards things that are more useful for model selection. And these things are actually distinct from each other. Is something we've come to understand. But it was nice to see a bound that I think is explanatory and gives you non-vacuous bounds. Not impressive, but non-vacuous nonetheless. So secondi. So we're going to turn this agnostic bound into an oracle inequality. Actually, I might do that already in preemie. And we'll get the risk of the Gibbs posterior sample no more than any teacher's risk plus some size penalty. We'll introduce this notion of complexity, rewrite the bound. That's really what we do in secondi. And I'm probably mispronouncing the Italian. I should have asked Google Translate how to pronounce the Italian. I realize now too. And I would say like our investigation of trying to look at how these things line up with empirical results suggests that the scaling law is growing faster than some polynomial. That's, I think, what we can say maybe when we look at trying to line this up with empirical data. All right, and then for dessert, I'm just going to skip to English. We don't really want teachers. So I'd say actually the idea of comparing to individual teacher networks is not the right way. And that's why we run into this quantization problem. And I would argue in this talk, this is the way we're thinking now, that we want to think about not teachers, but distributions on teachers or stochastic teachers. And this is going to allow us to avoid quantization by making some kind of bits back argument. And then C epsilon gets more complicated. But I won't really have time to go into that. Okay.
Could I ask a quick question?
And I'm 5 slides in.
So, like you said that you think that you need like a teacher which can't perfectly fit the data.
I don't need that, but I'd like to be able to relate my risk to that teacher.
Because I guess like the most common argument I've heard for why scaling laws are so slow is like that the data is super heavy-tailed, so that like you actually like your approximation error decreases much slower than 1 on square root n.
Yeah, I mean I don't know what heavy-tailed means. Like if my data are JPEGs, then they live in a hypercube that's compact. There's no heavy tail. So I don't think that's quite right. I think it's more about there's another type of like the probability density vanishing near the boundary. Things you would like sometimes call like Bernstein conditions or things like that. So it's about that most of the data are away from the decision boundary, but there is a non-trivial amount of data near some corner that you don't get to see very often. So as you drive your epsilon your risk very, very, very small, you eventually have to resolve the decision boundary in some region which you haven't received much data from. Yeah. Good. All right, so here's some notation. We have labeled data. Those are going to be z's. Predictors are going to be thetas. Loss function, think about like classification loss. Our unknown distribution mu. Risk function is pretty essential. This is our expected loss over, like this is like what you're measuring with test error. A data set is S, composed of our samples. The empirical risk is the essential object in this talk. So this is like how well, what's our average error on the training data. Of course, this is an unbiased estimate of this for a non-random theta. But once you start optimizing theta, there's bias. And then we'll also talk about distributions on the parameter space. So posteriors will have a hat because they can depend on the data, and the priors will have no hat because they're soon to be non-random. All right, so the starter. So Buzaglo et al. Is this work that motivated us, and they were themselves motivated by two seemingly contradictory findings. So first of all, say a classifier of theta interpolates the data if the empirical risk is 0. So theoretically, SGD is known to introduce implicit bias in some learning problems, and we know this is important for generalization. At the same time, empirically, we can randomly sample an interpolating neural network, and it will generalize. So here's a picture. We have all neural networks. We have the set that will fit, you sampled training data set. Here's a set of all neural networks that fit the training data set well. We know that there are some nasty neural networks in here that will fit. But if you pick one at random, whatever that means, it fits well. So whatever measure we're using to sample, it seems like it assigns high probability. Now, this on the surface of it doesn't seem to like introduce any notion of implicit bias. In some sense, we'll see that the parameterization induces the implicit bias. All right, so Buzaglo et al., they introduce a few assumptions. One, they work under this realizability assumption. They're going to assume there is some network in your space of neural networks. So fix some neural network architecture. Some network in this architecture you're looking at is assumed to have 0 risk, which means if it has 0 risk, it's always going to have 0 empirical risk. It will never make a mistake. And they're going to work also with a kind of finiteness assumption so they can have a uniform distribution. But for just this part, actually, we can kind of like ignore these two particular choices here and instead say, let's fix a prior. This is the way we're going to generate neural networks at random. Here are the neural networks, theta star, that have 0 risk. These are like the really good ones. And I'll just make this assumption, which is more general, weaker than these two, or implied by these, which is that the prior assigns positive mass to this set of like really good networks. Okay. So I'm going to erase this, move this up. All right, so a random interpolator. What does that even mean here? So write theta hat. So hats are usually going to indicate that something's data dependent. These are the networks that achieve 0 empirical risk. So it kind of stands in comparison with this theta star, which is actual 0 risk. So obviously, these two things are going to be nested. The ones that contain 0 training error are going to contain the ones that have actually true risk. Okay. And so the prior assigns amount of mass to the ones that assign 0 training risk because it's lower bounded by the amount that have actual risk. That's positive. So all these are positive. What that means is I can define a conditional distribution. I can condition the distribution pi on landing in this set of measures that have 0 mass. So that's going to be our notion of like randomly generating and interpolating predictor. If you remember elementary probability, it's just given by the ratio. I'm going to take the prior, I'm going to restrict it to theta hat, I'm going to renormalize. And later on, this is going to be a more useful way of representing this action of defining a posterior. Here, the indicator is throwing away everything outside of the interpolating neural networks and renormalizing. These all mean the same thing. All right, so what's the risk of a theta hat sampled from this rho hat, this randomly generated thing? So I'm going to erase this stuff, move this up. So Buzaglo et al. Kind of make this observation. If give me an IID sequence of samples from pi, let kappa be the first one that lands inside this interpolating set, inside the first one that fits the data correctly. Then this one has the distribution of the posterior, the one that we are seeking. Okay, so this is sort of like a guess and check procedure written out. All right, and this kind of motivates a potential statistical analysis, which is that, okay, let's look at the first k being some large number. I'll ask, hey, among the first k and among those in the first k of these that have 0 training risk, what's the largest their risk be. And you can prove using uniform convergence, like very standard arguments, that with high probability, this will grow as like tilde O hides log terms, like log 1 over delta terms, log k over n. So it's very mild dependence on k. And then you notice that, well, OK, that's fine. So I just need to choose k big enough that's likely to contain kappa. And then I'm done. And indeed, kappa is going to be less than 1 over the probability I assign to interpolation with high probability. Now that's conditioned on this. I want it unconditionally, and so I can just replace this by its lower. I can replace this by its lower bound. Okay. So what does this all mean? It means this. Let theta be a randomly sampled interpolating neural network. Then under some conditions which are unfortunate but mild, the risk of this interpolating classifier is log 1 over the probability of the prior sampling from this awesome set plus with high probability over n. So, all right, so I kind of reduced the problem of figuring out how well does this work to how much probability does the prior assign to this super nice set. All right, so quick aside, I'm just going to use this as an opportunity to introduce PAC-Bayes to you all. Because there's a kind of a slicker PAC-Bayesian proof. In their paper, they actually say you can't prove this with PAC-Bayes. But that's not true. All right, so here, just some notation back for you all. So let's let theta hat be a sample from rho. That's what I've been saying so far. So theta hat, condition on the data, is a sample from this data-dependent posterior. Okay, this is our model here for a randomly sampled interpolating neural network. So PAC-Bayes, at a high level, and I'm trying to encompass like the full scope of PAC-Bayes because it's like much broader than it was originally kind of introduced in the late 90s, is a way of making comparison between the random variables, the risk of this random choice from this posterior, the empirical risk of this random choice, and this quantity called the information density, which looks at the ratio of the density between rho hat and pi at this random sampling point. Now, classical, if you open up something in PAC-Bayes, generally you're going to be making comparisons not between these random variables themselves, but by their conditional expectations, or think about integrating this quantity under the posterior itself. But there are these very nice so-called single sample bounds, and Cotonyi has like the nicest of them. Now this is inscrutable, believe me. When I first read this, this book was useless when I first picked up this book like 10 years ago. What a useless book. It's like one of those books that like only experts enjoy, you know what I mean? There are many books like that. Now I enjoy it. So so this is indeed doing what I said. It's making a comparison between the risk at theta hat. Theta hat's the same thing I've been talking about, a randomly sampled interpolating network. It's making a comparison between r theta hat, the empirical risk at theta hat, and the information density. Okay, we just have this like function here which is totally inscrutable. But let me just simplify it for you. If you were to permit me, which you're not exactly allowed to, but you can sort of do it. If you were to permit me to optimize this lambda value, then this kind of nightmare here simplifies to something like this. And you could also simplify it to something that doesn't have this thing and just has a square root here. Anyway, so this looks totally standard. That would say the risk is less than the empirical risk plus 2 times this term, which is behaving like a complexity over n, plus square root of the complexity over n, but you get to multiply it by q, which means that if q is very small, then this term kind of vanishes. So that's how you get something like a fast rate. Okay. So this is a single sample bound. The short, to summarize, for those who are joining late, just kidding. To summarize briefly for everyone probably, at a high level, it's allowing me to make a comparison between the risk and the empirical risk and this information density. And critically, it's for the point sampled from this data-dependent distribution from the posterior.
Sorry,
where is there a D? This is just generic. This is like for all Q, D, and lambda, or maybe not lambda because lambda is being infimum here. You talking about this D?
Yeah.
Yeah. It's just this. You think about this statement as being quantified for all D and Q. This is true. So D in this would be this part, and Q would be this part. So that's how you would translate here. All I'm saying is this to many people, even like people who have worked in statistical learning theory for a very long time might look mysterious, but it actually translates to some sensible looking bounds. All right, so let's just go back. So let's assume we have empirical risk is 0 almost surely under this model, which is the case for us. Then what this Catoni bound says as a corollary is that the risk is less than the information density plus log 1 over delta over n. And if we look back at our starter with the side of PAC-Bayes now, what is our posterior? Our posterior is this object. This is saying toss out anything that doesn't interpolate. All right, so this is conditioning on interpolation. All right, so by construction, this thing fits the data perfectly. By construction, what is this logarithmic derivative? If I sample from the posterior, well, if I sample from the posterior, this is always 1. So this is just a constant. Oh, that should be a hat. I guess that should be a comparison like greater than or equal to. All right, so what's the question we started with? What's the risk of this? And the risk is this. And this is just a cleaner version of what Buzaglo had without any conditions on delta, which is that fix your prior, assume you have pi realizability, meaning that you're assigning positive mass to the good networks that have zero risk. Now sample a randomly generated interpolating network. Then with probability at least 1 minus delta, or you can just say with high probability, the risk looks like log 1 over the probability of sampling one of these good networks over n. Okay. So again, so this is just cleaning up constants, but maybe serves to show a new PAC-Bayes bound, which like maybe people haven't seen, but it's quite nice, and I've been thinking about using these for a while now. All right, so okay, what else did Buzaglo have to do? Well, Buzaglo had to bound this quantity. All right, so let's take a look at that. So what's the lower bound on this probability of sampling a good network? All right, now on the face of it, it seems like a bad idea. I'm going to sample a large neural network, and I have to sample a good one. Like that seems astronomically small. But just pay attention. The risk looks like log of that, right? So log turns numbers that you don't want to deal with into numbers you are okay to deal with, right? And that's what's going to happen here. So just some notation. For network theta, I'm going to let m of theta be the small. This is a tricky idea. The smallest number of parameters we must specify to produce a network that's functionally equivalent to theta. It's a slightly weird idea. I came up with it last night because I had to compactify a lot of stuff onto one slide. Okay, so let's say I had this network, and say I'm asking for the m of this network. But this network has something clever has happened here. I think this is orange. These orange ones are 0 weights. What that means is it doesn't matter what these weights are. Okay? And these were made 0. These two orange ones, and so it doesn't matter what these weights are. And so actually, really what I'm specifying here is something of this architecture. And so the number of parameters, the real number of parameters here are the parameters for all these weights and the specification of the zeros for these 4. Okay, so that would be your count. The size of this plus 4. Got it? Okay. It wasn't that hard. So this count here looks like number of parameters in this, what I'll call the teacher network. This is going to be the thing that's smaller, plus the order of the neurons in the student network, which is larger. And it's actually kind of you're just counting where these zeros are, but it's on the same order in the worst case. Okay, so now Buzaglo et al. Introduces a number of assumptions. One is that they're going to work with quantized neural networks. That's just going to make their lives much easier, made our lives easier too. We're going to take that assumption and run with it. And 0 is going to be one of those levels. Why? Because I want to be able to turn off neurons. I need to be able to turn off neurons. We're going to make this, now this is a, let's see what you think about this. I'm going to assume that there's a Batch norm-like initialization, meaning that the weights leaving each neuron are multiplied by a neuron-specific scaling weight. So let's think about how would I turn off these 2? 1, and let's say rather than 2, I had like 100 of these oranges coming out. I would have to specify 0, 0, 0, 0. I'd have to specify as many zeros, which is going to cost me log q bits, as I have orange lines. Now, if all the neurons coming out of if all the weights coming out of this neuron have a pre-multiplier, which is also a parameter, I can just turn that pre-multiplier to 0, and I kill everything leaving the neuron. Okay, so this, and apparently, I'm not really an expert, but apparently when you initialize batch norm, it kind of behaves like this. I'm not sure, is that true? So apparently that's the case. But you can imagine, now you can imagine I've just made it much cheaper to encode to turn off a neuron. Okay? And if you parameterize in that way, then you get the results that I'm about to have. If you don't parameterize in that way, if I had to turn off each of these neurons, then at least the naive kind of argument that we have, or really it's Buzaglo's, would pick up a kind of a dependence between the not quadratic in the dimension of each like a layer in the student, but it would be kind of it would be something that kind of, it's like this is A and B, it's not A squared, it's like AB. But I want BB. I want B squared. All right, and then finally, they're going to work with a uniform prior over the quantized networks. And then the upshot of all this is, and it's not so hard now to come to this idea, I've given the idea, like, okay, to get to this network from this network, I kill these two, and then I'm done. So let theta star be an arbitrary one of these, say, good networks, then it doesn't even have to really be a good network, it's any network. Then log 1 over the probability of landing in the set is going to grow as the size of that network, the actual size, in the sense of the smallest number of parameters we need to specify times log q. Okay. Now we can return to the bound we had earlier. So let's assume we have quantization, batch norm like init, uniform priors, and pi realizability. Let's let m star be the smallest teacher network in this good set of networks. All right, so the easiest to describe zero risk teacher. Let S be an IUD sample. Let's let theta be our random interpolating network. And then plugging it all together, what we have is that the risk is less than m star log q over n with high probability. All right, so there we have basically, so here's another way of writing this. If you give me a number of samples which grows linearly with m star, then that's how I can get less than epsilon risk with high probability. So normally, if you approach this problem, you would probably pick up a dependence somewhere on the. You would typically pick up a dependence on the size of the student here. So this is nice. All right, so that's Buzaglo. That was ICML this year. All right, so okay, praise and critiques. So it's a nice observation that this choice of parameterization, in particular this batch norm-like init, leaves us in implicit bias, even from what was meant to be uniform sampling. Of course, from another perspective, you can play this trick in other ways. For example, students and teachers have the same depth in their work, but it's not hard to dream up a parameterization. Indeed, we do in our paper for doing the same trick to deal with different depths. I just have a parameterization which easily allows me to skip layers. And then now I can skip layers. Things like that. Now, one downside of this is that I'm pretty sure you don't need to have this initialization to have neural networks generalize. And so they're relying upon something to prove their bound, which is not necessary in practice, and that's always upsetting. Posterior sampling, maybe it's not a great model. One of the big ones in my view is the realizability assumption, because I know that's just not compatible with how data behaves in practice. And indeed, if I want to get insight about what data is like, then I need to have some kind of trade-off between approximation and estimation. The quantization assumption certainly doesn't match practice, and it's essential in the argument. They have a Herculean kind of part of their paper where they kind of deal with continuous weights under this kind of invented margin notion. But it seems very difficult to extend further to more layers. And anyways, you can kind of ignore away the quantization problem by pretending you're working with float 32, but at some point it's going to rear your neck when you ask for an epsilon that's like 10 to the minus 20, and now your network can't actually fit that. And so the problem is actually real, because you don't want a big, huge constant in front of your bound, because then you're not really engaging with practice. So something is going on with how much accuracy you need, and if you're just ignoring quantization, kind of like this theory does, then you are not dealing with this kind of critical aspect of how neural networks work. Like things like flatness, et cetera, I believe are essential to what's going on with quantization. So this theory, of course, predicts faster rates than we've seen empirically, and that means we get to rule out this theory. Can't explain networks as that diverge in size. The student network has to be kind of comparable in size to the teacher. It can be like kind of quadratically bigger. It can't be infinitely bigger. Anyways, so a whole bunch of things you can poke at. But in some sense, Buzaglo et al. Was like one of those papers like, damn it, we should have written that paper. But it was kind of good that they wrote it because I would have never been happy with all these things that are wrong. But they did it, and now I get to poke at it and make some progress. So we're going to start with realizability, which will see us rethink posterior sampling as a model for SGD. It will lead us to new rates, et cetera, et cetera. So let's get going. All right, so Gibbs posteriors. So in the non-realizable case, that means that the set of networks that have zero risk is potentially empty. And so that means that the probability that we sample a network that achieves zero risk might be 0 with positive probability. Hence, there may be no posterior. So I can't even use posterior as a model for SGD when I don't have one of these teacher networks lying around. I need to find a different model. All right, and so the model we're going to use is Gibbs posteriors because they kind of model this kind of soft optimization via stochasticity. And we'll see it's well defined even in the non-realizable case. So what's a Gibbs posterior? So a Gibbs posterior is defined by a prior, by inverse temperature, by some energy here. It's going to be like the empirical risk, which is built on some data set. All right, and so the Gibbs posterior itself is going to be, we're going to always be denoting these by rho hat because they're going to be data dependent. They're a distribution on our parameter space. They're going to be a reweighting of pi. So it's going to drag the mass up in pi. It's going to raise the density of pi over here and shrink the density of pi over here. And the way in which it shrinks and raises the density of pi is described by the rate indicative derivative here. And it has this particular. I'll just highlight this. It has this particular form. It's going to the way in which the density at rho is going to modify the density at pi, roughly speaking, at theta, is that it's going to multiply by or shrink it by e to the minus beta r hat n theta. Now, what should beta be? You should think about beta being something like square root of n, the number of data. It's actually a pretty big number. All right, so this is the average risk. And so this is something that's, say, if theta were non-random, would look something like kind of a central limit kind of thing going on. Okay, and so things with very small risk are not going to be shrunk too much. Things with large risk are going to be shrunk by a whole lot. And so what's going to happen? The prior is going to have the posterior is going to downweight the mass of things that work poorly, and it's going to upweight the things that work well. Okay, so it kind of makes sense that I would want to sample from this distribution because it's focusing most of its mass where the risk was small. And beta is certainly directing how sharp that action is. As beta diverges, all the mass collapses on the minimizers. And critically, so this, I'm saying proportionally, there's this normalization constant when you define it on the nose, which is the integral of this kind of function, this energy exponentiated function. So. All right, so I've moved up the stuff up here. Just keep in mind. So for just a few statements about the Gibbs posterior, for fixed S, this Gibbs posterior converges to the hard posterior that we're sampling in the first section in the Antipasti, as the inverse temperature diverges. So as you cool things down. If we assume the prior is absolutely continuous with some density p, then the Gibbs posterior is a stationary distribution of Lagrangian dynamics with this drift. I believe I've written that correctly. Apologies if I've messed it up. Maybe there should be a minus here. So what's the point of this? The point of this is if you squint your eyes, many people have used Lagrangian dynamics as a kind of a model for what SGD is doing. So this is the Gibbs posterior describes the long run behavior of that, if there's some kind of regularization term. The Gibbs posterior also shows up as like a scaling limit of stochastic gradient Lagrangian dynamics, which is like SGD with noise being added. There are some limiting dynamics. They're like an OU process for SGD and SGLD in a fixed step size regime, at least when data and the number of total iterations and a few other things diverge in a particular way. These results, unfortunately, don't cover high-dimensional models. They're kind of like a small p, large n kind of analysis. But anyways, there's lots of models that lots of algorithms that end up having this distribution as a description of its end behavior. And here's one other connection. It's kind of nice from the PAC-Bayes perspective too, which is that the Gibbs posteriors above arise a solution to the variational problems. Find me a distribution which minimizes the expectation of the empirical risk plus some weighting of the KL divergence between that distribution and a fixed prior. And actually, we were seeing, I'm not sure how many people caught it, but we saw on Monday or whatever, we heard talk about natural gradient descent basically solving this objective implicitly, which I think is pretty cool. So that was like a literal algorithm that was optimizing this objective. So anyways, this is all maybe evidence that like maybe this is a reasonable thing to study. Okay. All right, so a sample from this Gibbs posterior we can analyze with a single sample PAC-Bayes bound. All right, so here's our information density. Okay, now remember the single sample PAC-Bayes bounds relates the risk, the empirical risk, and the information density where? At the sample from the posterior. All right, so let rho hat be my Gibbs posterior. Let theta hat be a sample from my Gibbs posterior. All right, then with high probability, PAC-Bayes gives me this bound. And let me just simplify things, because this is what we're going to do. We get this term here, which kind of suggests, oh, I can kill this whole term if I choose my inverse temperature to be the same as the lambda that I'm going to eventually use my PAC-Bayes bound. So I am going to do that. I'm going to take advantage of that, and I lose this term. So the empirical risk of theta hat has disappeared. So I have a risk bound, now only depending on the information, only depending on what was the, well, I guess the information density has been split up. So only depending on this term here, which is a kind of local entropy kind of term. Indeed, like, for the physicists in the room, the Catoni has like probably the book on this. It's a bit hard to get through. And I think it's called like the thermodynamics of supervised classification or something like that. So that might intrigue you. All right, so back to teachers. What does this have to do with teachers? Well, so again, we're going to continue taking inverse temperature to be the same as our PAC-Bayes parameter, lambda. And we have this risk bound. I just showed you this. Now, we'll see that this term here is an analog of this term, which showed up in our analysis of posterior sampling. All right, so we need a teacher lower bound on this local entropy. So what's it going to look like? OK, so pick an arbitrary theta star. Now, this is arbitrary. This is not necessarily, doesn't necessarily have good risk. It's just arbitrary. This bound will work for arbitrary things. Now, what's E theta star? These are like the set of doppelgangers. These are the thetas that have the same minimal model with theta star. Because if I sample any of these, then I've in effect sampled theta star. So here's the argument. Here's this normalization constant. I write it. Here's its definition as an integral. And I can just lower bound this integral by looking at the mass it assigns to this set. And on this set, they all behave like theta star. This is just really, I'm basically lower bounding this integral by its evaluation on one set, a set on which the integrand is constant. All right, so then I go back to bounding this local entropy. This is all elementary. Plug that in, and it boils down to this. I get another empirical risk popping out. So OK, it looks like there's no empirical risk here, but there is an empirical risk lurking inside of here. Right? It kind of makes sense. This thing was made up of empirical risk. So this particular bound pulls out an empirical risk at my arbitrary teacher, plus a term which is the probability of sampling that equivalence, like minimal model equivalence class for that teacher. All right, so I'm kind of back to I'm going to need a lower bound of teacher. All right, so what you have here is that this local entropy bound is indeed, this argument didn't depend on which theta I chose, so I get to take an infim over theta star of the risk plus this what looks like a new complexity term showing up, the probability I sample this equivalence class of teachers. No longer a teacher that has zero risk, just an arbitrary teacher. All right, so by the same argument, Buzaglo, the probability I sample this equivalence class is just scales like m to the theta star times log q. It depends on how many parameters I have to name. That's all it is. If I'm using this uniform prior, if I'm using the batch norm initialization. So this is probably too much detail for talk, but if I just define momentarily this theta double star, which minimizes not the empirical risk plus this complexity term, but the risk plus this complexity term. So this is a non-random quantity. Then I can just shift my object. So I had this object here, which is a bound on my local entropy. Of course, this thing lower bounds the same term with my theta double stars, and I can add on this positive term, still get my upper bound. But now I can move back to an infimum for by taking advantage of the definition of this one as a minimizer. All right, so what do I have? I have this. I have that there exists a lambda that's positive. So now what am I doing? So look at this. This is going to be the complexity term inside of my PAC-Bayes bound. And the reason why I couldn't optimize lambda earlier is because that thing depended on data. But now I've gotten rid of all dependence on data. So I have a PAC-Bayes bound. The object I'm studying is random, but I've gotten rid of all the randomness. And so I can optimize the parameter lambda. It's going to be somewhere between like root n and n. And I get this. I get the risk of this sample from the Gibbs classifier is an infimum over teachers of the risk of that teacher plus the size of that teacher over n. This is like a slow rate version. I can also get like a faster rate version, which looks like risk of the teacher plus complexity, size of the teacher over n plus square root of the size of the teacher over n times the risk inside. So if the risk vanishes, then this term vanishes. So I get my fast rate. All right. So we did like a really toy MNIST experiment here, just to like see are we even in the ballpark here. So what does this look like? I'm not sure if this would cut it nowadays. I can just shudder thinking about the NeurIPS reviewer too, who picks this paper up. But so I found a 2-layer MLP with 3 hidden units. I didn't want to have a lot of parameters. Only 3,167 parameters for MNIST on that. I trained on MNIST for like 10,000 epochs. And obtained a network with 0.145 risk. All right? And if you apply the fast rate bound to this, ignoring quantization, or assuming you had 4-bit quantization, you get this type of bound. Now, I didn't have 4-bit quantization, but my guess is I have quite a bit of wiggle room there. What I haven't done is, what I haven't done is the work for like trying to quantize it. But I'm pretty sure we'll be able to get there. Now, of course, my bound holds also for future data. So I merely need to like, I really need to multiply the number of data I'm going to run the Gibbs posterior on by a factor that deals with moving from 4-bit quantization to 32-bit quantization. Then this thing goes 32-bit, or maybe it's even float 16, right? So I do have a non-vacuous statement for like just training a Gibbs posterior on a much larger network, or I'm sorry, a Gibbs posterior on a much larger data set. So you do get non-vacuous bounds, yeah.
A very basic question: how do you
please.
keep your fast rate bound when you don't know m of theta star? Since it's a real data set.
Oh, but I do know m of theta star, because it's any theta star.
Oh, I see. So you can take an infinite.
Yes, yeah. That's a critical thing, right? This is magical. So what did I do? Like the fact that I used training to find my MNIST was sort of cute. I didn't need to do that. I could have randomly generated them. I could have solved some complicated algebra equation to find a network. Anything is fair game. Anything is fair game. So I just used training to find it. All right, so, okay, so keep going. So this balances teacher risk and complexity. One of the key implications here is shifting the Gibbs posterior allows us to deal with the non-zero approximation error, allows us to deal with non-realizability, and we have this kind of trade-off between complexity and fit. Okay, so now let's introduce this complexity term, C epsilon. So our oracle inequality that I just showed you, I call it an oracle inequality because I'm comparing my risk to the best of some collection of classifiers. Doesn't tell us how risk behaves as we get more data, because I don't know how that approximation error term, I don't know how that first term behaves, basically. So let's define kind of the function, the exact right function, get me what I want. So I'll let R star be the Bayes error rate, meaning like the best I can possibly do, like kind of noise floor. And I'll define the C epsilon function to be what's the smallest network that gets me an excess error of epsilon or better. All right, so this is reflecting the minimal network size needed for a given approximation error. All right, and not surprisingly, it's about exactly the term that's in my bound. Of course, you can do this for any bound you have. It's just like now that I have a bound that's in terms of a small teacher that fits the data well, it feels like very natural to do it because it's so damn interpretable, right? Versus a bound that depends on this norm of the weights. Like, okay, I'm going to measure the complexity of my data by like the size of the largest weight. That sounds kind of dumb. So, and this, this has, this is monotonically increasing and decreasing. Sorry, that was right. And at like 6 a.m. I changed it. See, don't make such changes. So, so with a bound, okay. So what do I do here? Oh, right. So this is just plugging everything together. So there, again, so this is saying, this is plugging everything together. So it exists a lambda that's positive. I have this Gibbs posterior. I have a sample from it. What's my risk look like? Infimum over epsilons. Now, epsilon's playing the role of approximation error. And then here is my estimation error for that approximation error. Now, this doesn't really tell me anything. I've just moved symbols around. But now it makes sense to, well, plot this plot. So this is a plot of like the log of the approximation error. And I'll get a certain size, and that size, as that constant increases, this plot moves like this. Okay? So each of these is that 1 over square root of n kind of plot. All right? And what's determining the rate at which C epsilon is growing and shrinking is determining this red line. The statisticians, of course, will understand this. So, oops. So let me show you up here. So like this is what I was showing earlier. If C epsilon is growing like polylog, you get this rate. It's growing polynomial, you get this rate. Okay? And the upshot is that the aim is we're going to compare this to data. This is a different looking scaling law than people are using, is maybe the crux. We're going to compare this to data, and if we find that the risk is decaying slower than this rate, then we get to rule out this as our complexity of our data. Data is more complex than that. And like the yeah.
The different lines correspond to different values of epsilon?
Yeah.
Okay, so essentially, so epsilon is controlling for the complexity of...
yeah, approximation error.
So this is essentially a scaling law.
Yeah, I mean, there's no compute here.
Yeah, yeah.
So, let's see. All right, so last bit, dessert. So Donsker-Varden offers potentially a more sophisticated lower bound on local entropy. So remember we had this term. And I lower bounded it by the probability you assign to, I picked a theta star, I picked the doppelgangers, and I said, well, oh, it's lower bounded by the probability you sample one of those doppelgangers times e to the minus of the risk of that thing. But Donsker-Varden is exactly this variational definition of the local entropy. It says this is equal to infimum over measures on the parameter space of the average of the empirical risk under that measure plus a KL. Can't do better than that. Right? And so if you plug this in, you get this sort of interesting observation, which is that there exists a theta, lambda positive. If I let rho be my Gibbs posterior, and I sample from it, then the risk of this Gibbs posterior is an infimum over the stochastic teachers of the kind of stochastic teacher's average risk plus the KL between the rho and pi as our complexity measure. All right, so I'm not going to dig down further into this, but how is this going to end up looking at all like we've been doing before? Well, let's take rho to be, say, a Gaussian. Gaussian is kind of a mean, and what's going to deal with quantization error is going to be variance around that mean. If I have large variance in some direction, that means I didn't need to use many bits of information to encode that direction. So I have low quantization level, few quantization levels. If I have very tight Gaussian variance, there's very little variance in some direction, that means I need to have high precision in that direction, right? And this comparison with pi is going to dictate the cost of choosing these different scales. All right, and there's also going to be a cost that I'll pay for the location. Now, the real way you don't want to do this is not by having pi be the same as your initialization. That's not the right way to get the bounds. The right way bounds is actually try to do something called localization by choosing a prior that depends on the distribution, but that's too complicated. All right, so I'm done. Basically, just a few slides that Claude helped me write. God help us. Let's see. Okay, that's reasonable. So this work bridges theory and practice in deep learning generalization. This is pretty bad, isn't it? Claude, you screwed me. Yeah, let's skip that one. Yeah, it's dumb. All right. So, all right. So I tweaked this one a little bit, I think. So we've introduced this new perspective on data complexity. I mean, in some sense, like it's a usual one we might do in statistics, right? If we have a bound based upon the Holder smoothness of your class, you can measure the complexity of your data in terms of the Holder smoothness. And I think that's kind of dumb. But like, I think the idea that like, oh, hey, maybe neural networks work well because like small versions of them work well. and we don't pay too much for over-parameterization. That seems kind of right. I mean, it relates a little bit to lottery tickets, which Caroline and I have worked on. It relates to a whole bunch of ideas. So I like this. So we have this new way of measuring data complexity, very natural, inspired by these bounds. We've actually done early work on seeing if we're anywhere in the ballpark of explaining generalization of some data sets. I think there's a lot more there. And doing this with quantization was going to be hopeless. That's why we've invented the stochastic teacher thing, because I actually think that here's the funny thing. Back in 2017, we were optimizing Gaussian neural networks, stochastic neural networks, to find non-vacuous generalization bounds for neural networks. What this bound tells me is that algorithm that went looking for stochastic neural networks with small generalization error was essentially bearing witness to the generalization of a Gibbs sample from the Gibbs posterior, which I think is an interesting thing that I did not anticipate, surely. I'm pretty sure, you didn't either. So, we didn't know that back then. We hardly knew anything. But yeah, so, we were always concerned with, these Gibbs posteriors are not really like SGD. That's too bad, but still isn't interesting that we can find these very big Gaussians with small KLs. Well, that's what we're doing. We're essentially finding witnesses for this infimum that were non-vacuous. So. I went backwards. OK, yeah, thank you.